Hi class, welcome back. Today we're taking a look at the second part of Unit M. We're going to continue on here with M7 and go through to M9, 9. So 7, 8, and 9. Now, where we left off last time was we were asking the question, which of the 6 explanatory variables are individually significant at explaining the listing price of a house? We're going to move from individual tests here to taking a look here then at aggregate tests. So it says here, whereas the individual t-tests are used to test the effect of a single explanatory variable on the dependent variable, the f-test introduced in the last unit tests the accumulative effect, or maybe a better word here then is the aggregate, so all of them together here, effect of all the explanatory variables on the dependent variable. So it's taking all the x variables as a bunch together. Similarly, the R-squared value is a measure of the percentage of the variability in the dependent variable that is explained by all the explanatory variables, all the x's, all 6 x's put together. However, it's still important to note that the R-squared will always increase as more variables are added to the model, even if this new variable adds little to explaining the dependent variable. What that means here is that I could take a look at the size of the house and the age of the house, the number of rooms and bedrooms and bathrooms and fireplaces and so on, and then I could add in here the lot size, which is probably important, and so on, and maybe a location variable, where it is in the city, which is probably important, and then I could look at the number of penguins which were born in the Antarctic last year, and I could take a look at the number of days that Prime Minister Trudeau wears a red tie, and I could take a look at, I could actually add any variable that I want to measure in there. And the thing is that the R-squared value actually will never go down. It will always either go up or have no effect when you add in useless variables. But the problem is that the variables start to fight with each other mathematically. They get all confused, and if there's any correlation between any of them, then they start to argue with each other. We'll talk about that in the next section called multicollinearity. So you can have too many variables in the model, and that is, it's not a great thing here. So what the adjusted R-squared value does is it's kind of a penalizing factor. And so it reduces the R-squared value if you have too many useless variables in it. And this is the formula that we have for that. Not sure if that's in your formula book. You might want to write that in there. And this, I guess, would be a check to see if you listen to this. But that's the adjusted R-squared, and we'll get to that in a moment here. But let's take a look at this question here, which is on right here on the top of page M8. It says, do all of the 6 variables taken together significantly explain the listing price? Notice the difference between that and the wording over here, the last one, which was talking about their individual impact. So back up here, let's take a look then at the f-test. And remember what I did last time is I drew this line here, right here, and it separated out the top from the bottom. And the bottom is where you're dealing with the individual tests, and the top is dealing with the aggregate tests. So there you've got the R-squared value, which we'll get to, which is an aggregate measure. And then the ANOVA test is looking at all of the x's put together and their effect on y. So that's actually what we're looking at right here, is the f-test, and we learned about that first in Unit S. So we'll formalize that, but let me just show you the output right here, and then we'll put it all down. So reading this particular output here, what we've got is, here's your SS values. So this is SSR, and this is SSE. Now another name for residual is error. And then this is the SST value right here for total. And then this label should probably be over here. These are the degrees of freedom. So this is P. P stands for the number of X variables, explanatory variables. So that's garages, square foot, days, rooms, fireplaces, baths. This is N minus 1. So this is your degrees of freedom for SST, which is 90 minus 1. And then this here is N minus P minus 1. And we saw that when we were doing the individual t-tests. That's 83. 90 minus 6 minus 1. Now, if you divide this big number here, 5.11, etc., divided by 6, you'll get the numerator for your F star. Here's your denominator, 2.48 times 10 to the 10th power divided by 83. You get this number, divide these two, and you get your F star value. And then here's the P value for your F test. And this P value then tells you that all 6 of them together significantly explain the listing price of a house. And we'll do a formal F test here, and we'll find that this F star value is way out there. It's quite high, and we'll end up rejecting HO. So those are the numbers that we're going to be looking at. I'm going to go and now write those in the space provided. So back here then on number 5 here, do the 6 explanatory variables taken together significantly explain the listing price of the house? So HO looks like this. The beta for garages is equal to the beta for square feet is equal to the beta for, let me see, days is equal to the beta for rooms is equal to the beta for fireplaces is equal to the beta for baths is equal to 0. They're all equal to 0 against the alternative that at least one of the betas is not equal to 0. Another way to write that is we could say all of the betas are equal to 0. It's important to have that word all in there, for I goes from G, SQF, D, R, FP, and B, to at least one of them is not. At least one beta naught is, beta I is not equal to 0. All right, so that's another way that we could write the HO. That's step number 1. Step number 2 is we're going to be using an F star formula, which is equal to SSR over P divided by SSE over N minus P minus 1. And we saw that formula back in Unit S, and it's in your formula book as well. Okay. Let's take a look at the critical value. So this is going to be an upper tail F test, and it's going to be based on 6 and 83 degrees of freedom. Those are the degrees of freedom for SSR and for SSE. Always an upper tail F test. There we go. So if you look under the 5% table, 6 degrees of freedom for the numerator and 83 for the denominator, you're going to get something exciting, 2.25. And then we did the test here, and we got the F star equal to something really high. It was 28.53. So that was 5.118 times 10 to the 10th power. I'll just use scientific notation there because it was a really big, long number. Divided by 6 over 2.481, is that? times 10 to the 10th power divided by 83, and that comes to 28.53. Just going to go back up here and, I guess I can just turn my page here and see what we get. Yeah, that's it. And that is way out here in the tail, and so we end up then rejecting HO. And that means that all of the x's together significantly explain the listing price of the houses. Okay. How much? Well, that's the R-squared value. So let's go up here now and take a look at the R-squared value. So the R-squared value then is this guy right here, which is 0.673. And then the adjusted R, I'll show you how to do that calculation, is 0.65. And this guy here, of course, is the SE value. And we're not going to use that. This guy here, if this were a simple linear regression, that's the square root of the R-squared value, and that would be the Pearson R if you only had one X variable. What regression actually does is it considers all of the X's together as if they were one variable. And it's the correlation then between that and the Y's. So that's what we've got there, but we don't use that measure. In fact, I'm going to just delete that circle. So we're taking a look at those two orange guys there, the 0.67 and then the adjusted R-squared. So let me go back down here. And say, so the R-squared value then was 0.673, or 67.3% of the variation in listing price of houses is explained by the 6 variables together. The adjusted R-squared value is found by this kind of goofy formula. It's at the bottom of page M7, and so it's equal to 1 minus, and then there's an adjustment here for degrees of freedom. It's 1 minus R-squared. And so that's equal to, in our case then, let me just get rid of some of these guys here. There we go. Is equal to 1 minus 90 minus 1 over 90 minus 6 minus 1 times 1 minus 0.673. Now that's already a squared number, right? The R-squared value. And so that will come out to 0.650. What this is it's when you get the adjusted R-squared value lower than the R-squared value, it means that you've got some variables in there which are insignificant. It's kind of a penalizing factor. If they're all significant, it might be a little bit lower, but it should be pretty close to it. So that's what we've got. We still, in calculations, use the R-squared value, not the adjusted R-squared value. Hey, one last thing I want to show you before we leave this page here. And now that we've got the R-squared value, so this is kind of an aside here, but it ties these two questions together, is remember I said that The f star can also be calculated. This was back in Unit S, using R-squared values. So it's R squared over P divided by 1 minus R squared divided by n minus P minus 1. And so if you put in here 0.673 divided by 6 over 1 minus 0.673 divided by 83, then you'll get 28.53. It's equal to 28.53. So there you go. All right, I'm going to end that there. We will pick up this whole thing about the assumptions of the model next time. And so let's call that, well, that only went to M8. That's okay. Oh, you know what? No, I am going to continue on. Sorry, that's not. Let's continue on here. So the assumptions of the model. Remember, we talked about these in Unit S here. And it says that these are 4 assumptions that must hold when you're dealing with the regression, that the error terms are a random variable with a mean of 0, an expected value of 0. That's actually the actual e's that we get here are normally distributed, and they have a mean equal to 0, so that's not a problem. This one here, the variance of the e terms, remember the term that we use for that? Is we were talking about something called homoskedasticity. Skedasticity. I think there might be an S in there. And if there's a violation of that, then we say that it's heteroskedastic rather than homoskedastic. And then here, so a violation would be heteroskedasticity. And, maybe I shouldn't do it that way. Let me just back up here. Yeah, so they're homoskedastic then if this condition holds. And then this one here, the values of the errors are independent. And so that means that there is non-autocorrelation, that the y's are not correlated with each other. If they are, then you would say that there's an autocorrelation problem or an autoregression problem. Now, that's something that we tend to test when we're dealing with time series data. So again, if we're looking at something like as the years increase, how does the GDP or the change, then that is a good candidate for testing autocorrelation for time series data. I'm just going to take a look at number 2 here. And then number 4, which is that the error terms are normally distributed. And so down here, I've got a couple of little plots here. This is a normality plot, which a lot of stats programs give you. You can actually do that with Excel in terms of plotting the residuals. There is an option there in Excel for a normality plot. And the other thing we could do is to use an Anderson-Darling normality test and find out if they are significantly different from normal. With a normality plot, if they're all on a straight line like this, then you're good. Looks like there's one outlier out here, but they're almost all on a straight line here. So that's fine. The second condition then had to do with that heteroskedasticity, and it looks like there might be a bit of a problem here, and that is if you take a look at the error terms, you see that there seems to be kind of a divergence that tends to happen. Not sure if there's enough here to really check, and so there is a way to go further and do a check on that, but that's something that we're not going to do in this particular course. But again, you could go to an advanced stats book or pull in a statistician or something, and they can check that for you. Multiple regression model must also satisfy 2 other conditions or assumptions here, and this first one here, this one actually works for simple linear regression as well, but it says here that the number of regression coefficients to be estimated p plus 1 must be less than actually the number of observations. Now, that's kind of goofy. What that says here is that in our case, we had 6 variables. And 6 plus 1 is 7 because we've got a y variable. So the number of observations has to be more than 7. Well, of course it's going to be. If you think of a simple linear regression model, it says here that the number of observations must be greater than 2. 2 just makes a straight line, and if you just had 2 points, you get a perfect straight line, an R² of 1, and everything kind of craps out in terms of its calculations because your standard error, which is in the denominator of your T star formulas and in the bottom of your F star formula and so on like that, it turns out to be 0, right? You'd have no error. And so when you have an R² of 100%, that's a great thing, but all the points are on the line and it actually craps out at that point. That's what would happen if you only had 2 points in a simple linear regression line. So you got to have at least 3. And here, in our particular case, you've got to have at least 7. So, of course, we've got 90. This is a more important one. And this is that there's no linear relationship between the pairs of independent variables, and none of the independent variables are linearly related to a linear combination of the remaining x variables. We're going to talk about that next. That is a violation of something that we call multicollinearity. When you've got multicollinearity, which means that there is a relationship between the x variables, then that can be a violation of this condition here. And we're going to look at that actually in the next lesson. So that's where I'm going to end the lesson. That takes us through to the end of page M9, and we will